everyone. We are going to start with the popular talk now. We are pleased to have Professor Manisha Padala with us today. She is an assistant professor of computer science at IIT Gandhinagar. Her area of research is in the intersection of machine learning and fairness. Today, she will be speaking about LLM bidding markets. Let's welcome Professor Manisha Padala.
Thank you, everyone. I hope I'm audible in the back. So I'm from the CS department. I'm sure you guys know more maths than I do. But I'll try to give a flavor of how we use some of game theory and mechanism design in our research work. Maybe, I don't know, how many of you have heard of auctions? Almost all of you, right? So I'm sure a lot of you won't be really studying it in detail. But, and how many of you have used LLMs or use LLMs every day for, okay. So I was wondering, how many of you have the Pro and the Plus subscription for all the LLMs? Okay, all the rich people. Right, so it's expensive, isn't it? And we have so many different options to choose from. I don't know, which is your favorite LLM that you use? All of you, Claude? Anybody prefer something else? Gemini, okay. Anything else? So imagine you wanting to, Perplexity is like, yeah, the router thing. So today the talk is somewhat like that. So imagine you would want to, use different LLMs because they are good at different things. Maybe Gemini is good at, what is Gemini good at? Okay, Claude is probably good at coding. GPT is, I don't know, good at philosophical answers. I don't know. So you want to sort of explore all of these things, right? So how would you do that in a good way without actually having to pay each of these platforms so much, right? Is it even possible? So before we go there, I have a question for all of you guys. So we use Google, right? We've been using Google since a long time for free. So how do you think Google is sustaining itself? Advertisements, right? So is everybody familiar with that? So the ads that you see is what is making the revenue for Google. So how does Google decide if it shows an ad, right? So because it is offering a space, it's like property, like land, just like that. It's a land on the screen, right? You're assigning some particular space to a particular advertiser, right? Let's say Myntra. Myntra is displaying some of its ads. So how much should really Google charge for it? How do you decide? So if there is a commodity that I'm trying to sell, I have some manufacturing cost and transportation cost. I have an idea of how much to sell it for. But if it's just a virtual space in your screen, how much will you really sell it for? How would you decide? That's fine. Let's say they want to run. So for unit time, how much would you sell? Right? What would be the unit time cost? Seems tricky, right? So for all of these people usually, I'm not sure if there are many other ways, but for sure, one of the ways that Google for sure does this is auctions, right? You don't know what this has. I know you don't, but I'm telling you, okay, oh, it has got something very, very nice. But I don't really know how much to, if I say 100 rupees, maybe all of you will just go. If I say 0, maybe there'll be a commotion for between all of you to come and take it. So I don't really know how much to put up, how much of a price should I put for this. So what do? I conduct auctions, right? So that's the idea. So we will try to see the basic idea of auctions, and then we will try to see in future, this is a futuristic problem statement, maybe LLMs, could come and bid and make the market better for us, right? In terms of how much we are paying, right? So that's the idea. Any questions? Okay. So the talk will have the following topic. So we'll first So auctions is essentially one specific instance of something which is known as a mechanism, right? Anything is a mechanism. There is a specific definition of what a mechanism is, and auction is one kind of a mechanism. So we will try to see what is auctions, right? What is the problem that it is fundamentally trying to solve, and why is it so important for us? Then we will look at some very simple auctions, and then we will connect it with the LLM space, right? That's the agenda for today. So let us see what a mechanism is, right? What do we really mean when we say we are trying to design auctions? So here is a mom. She has a cake, and that cake has different toppings and different layers, right? There is it's just one cake, but it's a mix of chocolate, strawberry, butterscotch. Maybe some of the toppings are gems, some of the toppings are cherries, etc. Now the mom has two kids, and she does not know which kid prefers what, right? But she has to distribute the cake between the two in a way that both of them are happy with whatever they have received, right? So she does not know what, and it's, let's say, quite cumbersome to actually go and ask you, what is it that you like? What is it that you like? And if I go and ask whether you like it or not, will people always be truthful? They will just lie and stuff. So how would you divide the cake between the two kids? So what is the problem with when you ask who wants what? Even if they choose the same, let's say both of them like the cake equally well, then you will just divide it into half, then no issues. But they can say, I like something more than she likes, right? If I like the whole cake more than she likes, then do you think the whole cake will be given to so how do you define the, so if you ask, I can just lie, right? Because I wanted to, because I'm scared that she might like the strawberry that I like, so I'll just assign a very high value to it. I might just lie about what I like, right? So you want to divide, which is why I'm saying let's not get into the business of asking. If you get into the business of asking, people might lie. So people lying is the core concept here, right? So the idea is you want to design a mechanism where people are happy and people cannot lie about what they like, right? So one idea is, between the two kids, you choose one kid, ask that first kid to cut the cake into two pieces, right? The first kid is going to cut the cake into two pieces, but only the second kid will get to choose first. Oh yes, oh sorry. What I put it in, okay. Right, so if the first kid who gets to cut the cake knows that the other will choose first, so he will carefully cut it so that the first kid values both the parts equally, right? Because it doesn't know which part it might end up with. And the second kid will anyway get the better piece, the piece that it likes. So are both of them happy that way? Did you need to know which part they really want, which part they did not want? No, right? So this is hassle free. So this is mechanism, right? When the preferences of people is unknown and you want to design a rule, a system that will make them happy or some other objective, how would you do that? So this is the problem of fair division. So this is one mechanism. Like that, you could think of this as designing rules, right? In general, you want to design rules to ensure that agents who are strategic means they want better, right? They are always trying to get more of what they like. That's what strategic agents are, and they're very intelligent. They can really they're not two dumb kids, right? They know what to do best, so that the desirable outcome is achieved. So there are certain rules that you need to define. So the mother said, the first gets to cut, the second will choose. So the kids will follow the rules, right? They are not like malicious, right? They'll always follow the rules. But they are selfish and strategic. So they will, by being within the rules, they will try to the first guy will only cut it in a way so that it gets the piece that it wants, at least half, right? So that's how they are very strategic. And we need to be able to define a desirable outcome. In this case, the outcome the mom wanted is that both of them should be happy. That's the outcome. You could have different desires, right? So different outcomes. So for example, we could see the classic case of a voting scenario. So all of you would think that voting is very simple, right? It's also a mechanism. So what we don't know what all of you, which candidate is sitting in each of your minds. So what do? We try to select the candidate that majority of you like. That is the idea behind majority voting, right? So I'll ask you, actually, I will really literally ask you your preferences, which is the candidate that you like. You all give me the preferences. I count whoever has got the majority, I give them. So now what is the intention of majority voting? To select the candidate whom majority likes. But does it always lead to that? When will it not lead to that? So let's assume there is, so we can have ties, let's say. It's not like two people are getting the same majority, that's still a majority, right? And so let us think of a slightly different scenario. This is in 2000 US elections. So there were 3 candidates. So first, the election started with 2 candidates. One is George Bush and Al Gore, right? So only if George Bush and Al Gore were the candidates, then Al Gore would have won with a majority, right? Because majority of the people preferred Al Gore over George Bush. But what happened was at the last moment, a third candidate appeared, right? Who was definitely not the major choice, major person, but some of the candidates from Al Gore shifted to him, Ralph Nader, right? So because of that shift, George Bush actually won by 537 candidates. So among the 3 people, the one who won was George Bush, because people who preferred him actually voted for him. He was anyway never going to win, right? You get the point. So he's like a decoy candidate. So finally, the election was won by George Bush, but there is clearly one other person whom majority of the people prefer over George Bush. You get the see. So this is how voting. Voting is not really so people who actually, if people are smart and strategic, would they really ever vote for this fellow? No, right? So there is no reason why. So that, what is the conclusion? Like people are probably not that smart here then. But the idea is we are only studying strategic and smart agents. If the agents are strategic and smart, they would have never revealed their true preference of who they like, right? So, but the entire goal of designing a mechanism is to ensure that they really reveal their true preferences. So in auctions also, if a person has a certain value for an item, he should come and tell me that he values it at that. He should not arbitrarily quote a high or a low value. That's my intention. Only then I can get a good price for that item, because that's the value that it is generating in the system. But how do I really know what the value is the entire question. Okay. So mechanism design is just this, right? It is trying to create those rules that satisfy the objectives that is given, right? So that the individual agents who are interacting reveal their private information truthfully, right? So we assume that there are agents who are interacting with your system. They have certain private values which they might not let us. If they tell me, if there was no notion of private value, then you would run a simple optimization, right? You will just take their values and give whatever is best. Give it to whoever quote bids the highest or whatever, something like that. But because you don't really know what they value it for, because there is hidden information, you cannot run a simple optimization. You need something more, which is what mechanism design is doing. Any questions? Okay, so there is one. The mechanism has a common goal, but each of the agents have their own utilities, which they are, because they are strategic agents, right? They have their own individual utilities that they are trying to protect or maximize. So the applications for such a design is wide and varied. So first, of course, is Google auctions, right? Ad auctions. Then you have spectrum auctions. You have matching problems when there are multiple donors, multiple receivers, and each of them have incentives to lie about their risk, etc. So how do you really do the matching despite all of that, right? Matching so that you actually are able to give to the patients who are really in need, right? So that's one thing. The other thing is crowdsourcing, right? Crowdsourcing is when you're trying to you're trying to have your work done by multiple people, right? When you have, for example, in machine learning, data annotation is crowdsourced, right? You have a large amount of unlabeled data, the data that is not labeled, but you want people to label it for you. So what do is you put it up on the web and have multiple people label it for you. And you pay them for the quality of their work. If they label it very incorrectly, then you would pay them less. If they label it so you would want to so how much do you pay them for every label that they do? That again is not a very, it's an abstract thing. So which is why you need something like auctions, etc. Right? And any pricing for that matter would fall under mechanism design, etc. So the most simplest setup is a single item auction, right? We are all sort of kind of familiar with that. So you have a seller, he has a good, and there are n people interested in that good. So, and VI is the value that each bidder has for the good. So this is the value that I have if I get that item. And that particular value is private and not known to the person this is the mechanism designer who is trying to sell the good, but he doesn't know what is the value that these people have for that item. So what do we need to do? So first we need to model the utility of each particular agent. So if an agent does not really get the item, loses the auction, does not get the item, then the value is 0. He came with nothing, he's going with nothing. But if a person wins, right, then he will get the value that he had for that item, which is not known. And there is a price that he must pay. This price is set by the mechanism designer. So the rules in an auction are, who is the person who is going to win? Only one can win. This item is not shareable. So only one can win. Who will win? And the second thing is, what is it that they will pay? The moment you design these two things, that will define your auction. Okay? And when, based on that definition, these people will know what is it that they are going to get out of it, right? If they win and if they lose. Those are the utilities. So essentially we need to have, and one more thing to keep in mind is that it's a sealed bid auction. I do not bid my value based on your value. I don't know what your values are. So we are all simultaneously submitting our bids, right? And we don't know what the others are bidding. Otherwise, again, the dynamics change, right? And it becomes a more complicated set to analyze. And here the goal of the auctioneer is twofold: determine the winner and the price, right? That's it. So if I look at all the bids that are there, the first rule that comes to my mind is whoever has bid the highest, I'll just assign that item to him. That means that particular person values it more than the others. So I might as well give the item to the person who values it the most. But the main question comes in what should be the price that the person pays. What if I offer it for free? What will happen? What will people do? If I say whoever bids the high, I have this thing here. I'm saying I'm willing and you are all interested in this. Okay? It's probably your sheets or something. And I'm saying ki, I'll just give it to whoever bids the highest. What will you bid? A very small value? A very large value? You will bid infinite, right? All of you will bid very, very high value. So then again, so the question of who will get it becomes hard, right? So people are not revealing their true value. So you'll just bid the highest possible values. So we come to our first auction, which is known as the first prize auction. Here what happens is you determine the winner based on the bids. Whoever bids highest is the winner, and they pay whatever they bid, right? So what will your strategy be? Now you cannot bid arbitrarily high, right? Because you'll have to pay that, and maybe you don't even value it. So let's say you value it at 100. Will you ever bid more than 100? You will always run in a deficit, because remember, your utility is whatever value you are getting minus the price. So that will become negative. So that's not a strategic agent. A strategic agent would maximize the utility. That means he'll try to bid as low as possible. But if he keeps bidding low, then somebody else might become the winner. So it's not very, so you will definitely not bid higher than your value. You will bid lower than your value. But how much low, you don't know, right? It's not easy to figure out how much low. If I bid too low, I may end up losing the auction. If I bid, so what is the value that I should bid, right? So first prize auction is fine. People will not bid random values, but what agents should do is not very clear. They'll just bid lower than the value, but how much low is not very clear. So here is a slightly different auction, which is known as the second prize auction. So here, the highest bidder wins. The one who bids highest wins again. But this fellow has to pay the second highest bid. Doesn't have to pay his own bid. Has to pay the second highest bid. So now what will your strategy be? What should you bid in an auction like this? What will you bid? Highest. What is highest? Highest I will know when I know all of your bids, but you don't know what is the highest, right? You just know your value. What each agent knows is how much I value the item for. In first price auction, I'll always bid lower than the value, but I don't know how much low. In second price auction, what should I bid? If I bid higher than my value, what? So if the second highest has more than my value, then what will happen? Then you will end up with a negative utility. Exactly that value, okay. Any other answers? Okay. So this is known as the Vikri auction, right? This is like the... So what we know about this auction is that, like she said, I don't care about what others' values are, because I don't know it anyway. And I don't even care about what others are bidding. It is always the best thing for me to do is to bid my own value, which is a dominant strategy. So like in first prize, I didn't know what was a good strategy, right? But here I exactly know what my strategy is, and that is to reveal my actual true value, irrespective of what others' values are and irrespective of what they are bidding, right? So this is what is a nice auction, right? Nice mechanism, right? Just like we had it in the cake cutting, we didn't care about what values they had for the cake. The moment you run that mechanism, people will be happy. That's it. So the moment you run this auction, the person who values the most is going to get it, as long as they are smart enough to figure this out, right? That they should bid their value. So smart strategic agents run this auction and chill, right? And people also, if they are smart, they know it very well. What is it that they need to do? Okay, so let us see why, right? So let us see why. So just unlike this, in first prize auction, your best strategy depends on what others do. But in second prize auction, what we are claiming is that it doesn't. Irrespective of what others are doing, your strategy is always to bid your own true value, which is the golden standard for any mechanism. Truthfulness. People being truthful, revealing their private information is what we want. Okay. So let us see a small proof for this. So for a given agent I, let's say the agent I has a value V for that particular item, and B minus I is the set of bids of all the other agents, right? Everybody else has bid this particular vector. This is a vector of all the bids of other agents. Now, capital B is the maximum of all the others' bids. I value the item at, let's say, 100, and everybody sitting here are bidding. Let's say they have bid 10, 20, 30, 110, something like that. I will take the max of all their bids and compare it with my valuation. Okay? And then we will determine what I should be doing. So let's say capital B is the max of whatever they are bidding. Then, so what will happen if I bid less than the max? Then I'll definitely lose because I'm not going to get the item. I'm bidding less than the maximum bids. So in this case, I'll get a value of 0. But if I bid more than this value, then mine is the highest bid, right? So I will get the item and I'll pay the second highest, which is the capital B. So I get the item, so I get a value of V and I pay capital B. So these are the two possibilities. So now, what should I really bid based on how V and B are related? So in case 1, my value is actually less than the less than the bid, right? The highest bid that is there in the market. So what will happen? So the maximum that I can get over here is 0, right? So if I bid more than B, then what will happen is I'll get a negative utility, right? Because I'm going to have to pay more than what I really value it for. So I should bid less than B. I might as well bid my own value V, right? It doesn't matter, right? I can bid any value less than B, I'm happy. I might as well bid VI. So VI is very much part of the set that you can bid if your situation is here. And in that case, you can get at max a utility of 0. You know, in no case you will get a value better than 0, utility better than 0. So you in case 1, you might as well just bid your own valuation. What if it's case 2, when your valuation is greater than B, then the maximum possible value is VI minus B, and you just bid that, right? You just bid your VI, in which case you will get your. So no matter what the situation is, it is always good for you. It is always at least as good as any other strategy for you to bid your true value, right? There is no other thing that you can do which will get you something better, right? So, and it's very easy to analyze as well. Right? So this is a nice mechanism. Any doubts? Right. So this is what we want from an auction, right? Whenever we're trying to design an auction, we want that, in this case, my desirable property that I wanted was that the winner is the most worthy winner. The one who valued it the most should get it. And I get that from my Vickery auction, right? The highest bidder wins. That is a welfare maximizing auction. And I also want my auction to satisfy dominant strategy incentive compat. This is a big term for just saying that people should just be truthful about their value. And they will be, right, if they are intelligent. And then it should be an easy to think about auction. It should not be a computationally expensive or thinking, oh, is bidding truthfully the right thing to do for me or not? To just know that if you have to do a very hard problem, if you have to solve very hard problem, then that's also not nice. So you want all of these 3 things from an auction, and this does that for you, right? So that is just for a single item auction, and we want to try to do this in the LLM setup, right? But in an LLM setup, the things are slightly different, right? There are multiple LLM providers who are trying to provide you a service, right? So the first, and you are trying to maximize your own utility out of it, right? So you don't care who the most valuable LLM in the market is. You just want to ensure that you're not paying more than what you get, right? So for that, we will the entire idea remains the same. It's just the setup sort of reverses, right? So now what we are interested in is something which is known as a reverse auction, right? So in the reverse auction, the goal is slightly different. Now we want to select a seller. We are trying to purchase something. We are not trying to sell anything. But who should we purchase from, right? We can either purchase a particular item or a particular seller, a particular service, right? So who should we purchase it from? And we need to pay that particular seller or an service something, some amount of money. Even in crowdsourcing or something like that, this kind of thing works. So here what happens is, if I purchase an item from, let's say, person A, I get a value V. But if I purchase an item from person B, I get a value V prime. Right? I could get different values upon purchasing item from different people. And then they're, of course, selling it at different costs, right? Because of what they bid. So who should I buy it from, right? So that I maximize my utility, right? That is so what does optimality mean here? So when I want an optimal auction, I want to ensure that all the sellers who are trying to sell me something report their true costs. They should not arbitrarily quote a very high cost, right? So they should report their true costs. And as a buyer, I am trying to, sorry, there is a typo here, maximize my expected utility. So on an average, if I participate in multiple auctions like these, I should be able to get the service or the item worth the price that I'm paying, right? I should not choose a suboptimal sort of a seller. It may not always be the seller with the lowest cost, right? It depends on the values that we obtain. And also, because of truthfulness, if I always select the seller with the lowest cost, then that doesn't work here, right? So we would want also people not to lie about their true costs. They might just lie about their true cost if you have a very trivial auction. So this is the setup that we have. We have like 5 sellers who have their true costs. So seller 1 had cost 1 for procuring that particular item, right? And they are bidding. They are saying, seller 1 is saying, I'm willing to sell you the item for the price B1. Bidder 2 is saying that I'm willing to sell you the item for B2, and so on, right? So these are the prices that they are quoting in some sense. And the buyer has realized some values for these items. He says, if I buy the item from 1, I'm going to get a value of V1, and so on, right? So what do we, as an auctioneer, we need to do 2 things. We need to first find the winner. Who is it that I'm going to buy from? And the second thing is, what is it that I'm going to pay? So this becomes a slightly more complicated problem, than just the Vickrey auction. And without getting into much details, what happens here is that this is the final rule that people usually, the optimal auction follows, which was given by Meyerson. So essentially, I take the costs, right, or the bids in this case, BI, that the people report, and I compute this function, and whoever has the highest value of this, I will just buy the item from that particular seller. So this is something which is known as a virtual cost. All of this mechanism, why introduce all this PSI and all this business is because you want so that the CI becomes BI, right? We don't really know what CI is. So just so that they report what their true costs are, so that the BI becomes CI, you need to have all these mechanisms and transformations, right? So you'll have to trust me for that, but this does have a proof. So what do we essentially do is we compute the virtual costs, which is known as the virtual cost for each of these. It's like a threshold, you could imagine. If the particular person bids more than a threshold, then it is admitted, otherwise it is not admitted. So it's like you're running a second price auction, but saying, if the second price is lower than this, then I'm not willing to sell anything. Only if it is somewhat higher, I'm willing to, because you want to optimize your own utility as well. But the idea is that you just sell the item buy the item from the person with the highest value minus virtual cost, so the lowest cost person may not always win. And what is the payment? The payment is known as the critical payment. So this is the, I could report, so imagine all the costs of every sellers are lined, and one of the person's cost is such that I am picking that person. That person is the winner. Now that person could actually increase the cost more and still win to some extent, till the point it crosses the next highest person, right? So that the highest cost that that person can win, that can bid as long as he wins, is the payment. It's similar to the second price auction. The lowest bid that I can bid, as long as I still be the winner, right? So if I have a value of 100 and the second highest bid is, I don't know, 90 or something, I can bid 90 and still win, right? Because that's the second highest bid. So this is the same idea as that, right? So that is the critical payment. You essentially you report the highest cost, and which will still ensure you will ensure you that you're selected to be the seller. You just pay that much, right? So that's the idea. So this all of what this will do is it will ensure that people report their true costs and everything. So we already have a mechanism in place where users can maximize their utility, and people will be truthful. So how do we directly use it in the LLM setup? What is the challenge? What is the main challenge here? So in the LLM setup, each user has a query QT. So let's say I have a particular query in this case, and the platform has 5 different LLMs to choose from, right? 5 different LLMs to choose from. And this is the third party who is doing all this drama, right? Of trying to decide, pick and choose and pay. So let's say if you use LLM1, Zeta 1 is the cost that you need to pay, is the cost that this LLM incurs for spitting out one token, right? If it's a very large model, and it's doing a lot of, I don't know, chain of thought thinking, reasoning, blah, blah, blah. For every token, it is actually spending a lot of money. So that's the amount of cost LLM1 incurs. Similarly, every LLM has different architecture and different mechanism going on inside. So they'll probably have different costs in a very big abstraction. They'll probably have a different cost for every token that they generate. And this is private. We probably don't know. For a lot of proprietary sort of LLMs, we don't really know what is all going on inside, right? And for every query, these people decide to generate different amount of tokens, right? For every query that you have, different LLM will give you different length of the answer. The answer's length is also not specified. So let's also get that into the cost. Maybe we don't know, maybe they have some way of, keeping a knob on that, okay, how much to generate for every token, so that the answer is effective, right? So this is the number of queries per token. So the final private value for each LLM is the cost per token times the number of tokens, right, that they generate. This is something which is not known to us. It is just known to the LLMs who are providing the service. Well, NIQT, very honestly, is something that they also don't know, I guess. It depends on this, but there could be ways of improving the modeling, or there could be ways in which we could imagine that NIQT is something hard-coded in the LLM service provider, right? So there's a modeling in progress. Now, based on these private costs that they have for the query at time t, they will bid. They don't at this point. So this is a futuristic thing where they really come and bid. They say, okay, look, I'm going to answer this query for you at this price, B1T, B2T, B3T, and so on. And based on those prices, this fellow is going to now choose an LLM, right? Which to. And once this designer chooses an LLM and then provides let's say this person chooses LLM 2, only then will the user be able to say, okay, look, I am so happy with that answer, or I am unhappy with that answer. Let's consider binary reward. Either the user is happy with the answer or unhappy with the answer. So the LLM, the mechanism designer run an auction and etc. And charged PIT and the reward observed was RIT, right? Happy or not. So now, so now we can already see how it is different from the normal auction setup, right? In the normal auction setup, what we assume is that we know what the value I get with each of the item that is there, right? So V is known to me, which is why I'm able to compute max of Vi minus Psi I Ci. But now I don't even know what my V is, right? That's the biggest issue. Here the value of each LLM is unknown. And one more thing is that every time I change the query, the LLM which is good is going to change, right? It's not going to be the same LLM. So it's a query dependent value, and the value itself is stochastic. Also, every time you ask the same LLM, you may not be equally happy as well, right? You may get different values. So all of this you must learn. So this is where entire learning comes into picture. So you must learn which LLM performs well for what query. Only then you can then run your auction on top of it. Right? That's the idea, because there's no other way. Right? I'll be open to it if there are other ways in which people could do it. But this is the catch. So you have an auction setup in place where you can control the pricing to some extent. But the entire problem is you cannot directly import that auction here because you don't really know the values. The values are dependent on the query and they must be learned. So any comment about the setup here? Everybody is happy with the modeling, huh? Except that LLMs won't bid, I'm sure. Okay. So the idea is we need to learn which LLM is good for what to some extent, and should be able to pay them fairly over time. So here is a particular scenario where each of these LLMs are there and their rewards are stochastic. So on an average, you could imagine that the average is somewhere in the middle of the rectangle. So on an average, maybe LLM 5 is good, but sometimes it can give a reward of as low as this. Like that, there is this particular LLM which is on an average very low, but it could give as high a reward as this. So you would want to weed out all these LLMs and want to identify the LLM with the highest expected value, right? But in that process, what will you have to do, right? In that process, what will you have to do? You will have to explore each of these LLMs, right? Only then you will be able to figure out this LLM is bad, this LLM is somewhat good, this LLM is slightly worse, etc. Right? But the moment, that means what? That means you as an auctioneer, you as a third party are selecting all these LLMs randomly at some point. If you do that, people will just quote very high value, right? They will just charge very much because they know that you are going to have to explore them at some point, otherwise they won't be able to make a decision. You get the idea? So that's the issue. So you can learn if the costs are known, which LLM is, and the costs are fixed. Very nice. You can just explore all the LLMs based on their costs and value and decide what the value should be. But the costs are also strategic. You must conduct an auction so that people do not lie about their cost. But if you want to conduct an auction, you need to know what the value is. And if you learn the value, people will lie about their costs. So this is the story that you need to sort of get over, right? What can we do in this situation is what we are trying to see. So now very briefly, just to give you an idea of what is it that we do, but not really. I mean, it's a very, very high level intuition of what we do. So first of all, we do not guarantee, what we don't do is we do not guarantee that people won't lie every round, because people every round they may lie. But what we say is in 100 rounds, in 1,000 rounds, people are not incentivized to lie. So on many, many runs, people won't lie, but people might lie in each run individually. So we are in the expectation or in the probability space now. The values are, so for every query, I get a reward from a particular LLM Alright, so I try to find what is my expected reward, what is the average reward in some sense for a particular query, which I say is my VIT. And this particular VIT is unknown to me. The expected, the middle of the rectangle, this is that. I don't really know what that is for a particular query. So what I say is this is nothing but a dot product of some theta, which I don't know, and x. X is my input vector. I convert my input into an embedding, let's say, some vector in a high dimensional space, and I try to learn what this theta is. I don't really know what theta is. So this will tell me for a particular query, if I learn a nice theta, which it will map it to the value space. Exactly, the value that I get out of the L. This may not be true. Maybe theta transpose X is not enough to capture that dynamics. Maybe you need theta transpose sine of theta transpose X plus X square plus theta, some complicated function. But here we are just limiting it to a very simple function. We are saying that your values follow this particular function where theta is unknown. And here xt is the context vector. Thetas are unknown and latent for every LLM that is there. And you want to estimate the theta based on the history. Historically, I've pulled these LLMs, and this is what the reward looked like. So theta taking a value of 231 is good enough, is reflecting my values, or theta taking some other value is good. So this is the entire business. And for that, you have algorithms to do it for you, to learn thetas for you. This is well known, right? Yes. XT is the input query. So you have different LLM being good for different queries, right? QT is the query, and the vector representation of QT is XT, you could say. It's the
XT. All LLMs with XT is fixed.
Yeah, you're just asking one query for all the LLMs. So this theta I, so essentially if you take a max over I here, you will get an idea of which LLM to choose. Right, so that will give you the max value, but it will be different for different XTs. So this is essentially known as a contextual multi-arm bandit problem, right? You have multiple arms, which are your LLMs, and you are trying to choose the best arm. But your best arm depends on your context also, which is your query. So it's a contextual best arm selection algorithm. And so if you run that particular algorithm, you identify what these theta i's are, right? Theta i's are very effectively. And once you identify theta i's, you just run your mechanism, right? Your mechanism was saying Vi minus psi I of Ci, right? So now you just replace that with theta I transpose Xt instead of Vi minus psi I of Bi. Now we have to show that just because you run this contextual multi-arm bandit, people might lie. Just because you're exploring all the arms, people might lie. So you will have to somehow get rid of this Bi here and plug in a Ci, somehow be able to do a Ci. So okay, let's so that's the so in general what happens is in a multi-arm bandit problem, what people usually measure is how bad are you from the optimal arm. So there is one LLM which is very good for you, but you are not picking that LLM. You're picking some very bad LLM. If in capital T rounds also you're not able to pick every round you picked a very bad LLM, then you will accumulate a regret of T, right? You will get a very bad error of 1 in every round, right? You could have gotten a very good reward, you're getting a reward of only 0 at every round, and you will get as worse as T reward. So you want to be able to figure out the best LLM in much less than T time, right? You do not want to spend the entire T time selecting the best LLM. So people look for something which is known as a sublinear regret. So it should be strictly less than order of T, right? So there are particular mechanisms which try to give you sublinear regret, like sublin UCB, and but the only challenge is if you directly run these algorithms, providers will, or the LLMs will manipulate the cost while you're implementing this learning algorithm. So what we propose is a mechanism where people won't, the regret is still sublinear, but LLMs report their true costs. And the thing is that people they will report true costs in expectation, not in every round, but on an average, they will report their true costs. The rewards are, of course, stochastic and initially unknown, and it learns from the past queries, and bidding truthfully or reporting the true cost is optimal in expectation. Right? So how this happens is more of a technicality. It's just the Meyerson auction, but it is smartly implementing that Meyerson auction for the MAB, multi-arm bandit problem. Right? So if you try to smartly, like in a random way. So Meyerson auction, remember, was a deterministic auction, right? You always had a fixed winner. There was no randomness in the auction. If the bids are known to you, you know who the winner is and what the winner should pay. But here we don't have that. We have a random auction where the bids that I get from you will be randomized. Because I'm randomizing your bids, you don't really know if you will be the winner or not just because you quote a very high or a very low cost, right? And things like that. So that's what helps us sort of control the manipulation of the agents. And on top of that, we anyway have our MAB algorithm, which is giving us our sublinear regret. So that's the somewhat of the idea of how you do it in this case. Okay, so we essentially combined a learning algorithm with a truthful reverse auction to get a situation, to get a somewhat of a nice mechanism for us. But the only catch is LLMs are not going to bid. So we are still exploring any options where you could have all of these, but LLMs do not really bid, right? You have some other way of getting this done. Okay, so thank you. That's all I had for today. Any questions I can take?
Thank you, Professor Manisha, for the insightful talk. Are there any questions?
General doubt, the point of sealed auction. Won't it be better in the interest of anybody to conduct an auction wherein you can see when it's dynamic, because that's when you get the most profit for yourself. So why, or who even conducts sealed bid auction at this point of time?
Oh, so sealed bid auctions, spectrum auctions, government auctions are all sealed bid even till today. So, so why is a very good question. So I would not, so if you make it dynamic, it's theoretically not proven to give you better revenue than this sealed bid auctions. So theoretically, of course, theoretically, as in people are smart and stuff, which in itself is broken in the real world. So, but theoretically, what we see is that there is a revenue equivalence theorem. So all these different auctions that you can have a very complicated indirect auction run, but that will be as good as your sealed bid auction in terms of its properties. So you might as well study this. You implement whatever you want for other practical purposes, but you just study this, right? Analyze this. In fact, Google does not implement second victory auction. It implements something which is known as a generalized second price auction. Doesn't have the property, but works better. Yes.
What if two of them or three of them got the same amount?
There'll be a way of breaking the tie, but the tie break will not depend on them, right? What their bids are. So it is a tie. It's a tie. So if all the three of you bid the same, I say ki the person, I'll arrange your names alphabetically. The one with the least, like the lowest, I will always give. In which case there is nothing that you can do. Or I will say ki I'll randomly choose one of you and I will give. So how will you manipulate? You won't manipulate because you don't know if you are going to win or not. Right? There's no way of. So the easiest auction is randomly assigning the item to someone. How will people manipulate? There's nothing for them to do. Right? So like that, tie breaking will work.
Any other questions?
Yes. Yeah. The lowest cost. So we want, so value minus psi ci, right? That's what we, so we also want the item with the highest value, While it could be very low, the cost could be very low, but it may not be a valuable item to me. The person selling. The product is fixed. Not in the case of LLMs, but in the general case, it is fixed. So we will select the person with VI minus CI, the value minus. But directly using CI won't ensure truthfulness. People might lie about their costs. Just like if everybody will bid something and I choose the highest bidder, they will not really bid the true value, right? They will try to bid lower than their true value. Like that, if you fix and choose VI minus CI, jiska bhi zyada hai, usko you will give, then they will just bid arbitrarily lower cost or higher cost or something like that. So they will not be truthful about their cost. So to ensure truthfulness, you need to have that CI. So like you said, the product is fixed. Then I know what the value is. If the product is not fixed, every time I go to that person, the quality of his product is different. Then the value that I will get is stochastic, right? It's not deterministic. Stochastic means value is random. The value that I get from purchasing a product from you is not a deterministic value. It could vary.
LLM case depends on the query.
LLM case, it depends also on the query. So let's say you have T rounds to select the best LLM. Every of those T rounds you selected a bad LLM. Then you will get you could have gotten a reward of 1 in every LLM, but every round, if you had selected the best, but you're getting 0. So you have accumulated a guilt or a regret or a bad performance of capital T, right, for T many rounds. So if you give me a learning algorithm, which will give you a regret of less than T, then that's a better algorithm, right? As low as possible. Because then that means you have identified the best LLM after less than T rounds, much less than T rounds. And from then on, you're just picking the best LLM. So as long as it is sublinear, root T to log T, log T is the goal. So as long as it's lower than T, you're happy that your algorithm is working fast.
Constant times TIFR.
Yeah.
Okay, if there are no further questions, let us thank the speaker once again.
Thank you.